Welcome to Algebra 2, Semester 1, Unit 2, Parent Functions. We're going to be looking at a lot of graphing today. So let me get us to the very first. This is number 1 video. This video is Algebra 2, Unit 2, video number 1. It's on shapes and determining domain and range. So let's get into this. First of all, make sure you're using a pencil anytime you're graphing. In case you have some errors, you can go back and correct those. The very first graph that I have you graph, let me increase the size just a little bit here. Make sure that you can see it well. Whoa, not that much. Okay, basically the first equation is this y equals x. Now remember from functions that x is the independent and y is the dependent. So everything we do to x causes the outcome of y. X is our input. So in your t-chart, that's why x is on the left-hand side, is we input that number. Now if we have an equation like this where y is just equal to x, whatever's inputted on x is what we end up with for y. Now also from Algebra 1, we would take and make these into points, 0, 0, -1, -1, and so forth in order to graph them. Now if you can just see that visually here that these are the points, then you're welcome to just transfer them just like that onto the graph. Okay? Realizing that's your x and that's your y. In the graph, here's your x-axis, here's your y-axis. And so we go over, we find the x first and then go up or down to the y. So we go 0 right here. This is our origin, 0, 0. X at -3 would be -1, -2, -3 down to -3 on the y. Put a point. -2, -2, -1, -1, 0. Usually when I'm doing a linear graph, which is what this is, linear means line. It's just a straight line. I sometimes will just plot 2 points and then connect them with the straight line because I know that that's a linear function. It will be a straight line. Make sure to extend it across the graph with the arrow tips on each end. Now, our question off to the side here has been, what shape would you describe that graph as? It's a straight line. We'll come back to the question on domain and range in a minute, but we just want to get these lines graphed. Now we go to absolute value. Absolute value, as you can see, we input the x, but then the manipulation that we do with it is we take the absolute value. So the y is the absolute value of x. If you remember right, absolute value is a distance from 0. So -3 is 3 units from 0. -2 is 2 units from 0. -1 is 1 unit from 0. 0 is 0 units from 0. And 1 is 1 unit from 0. 2 is 2 units from 0. 3 is 3 units from 0. So when we go out and we put these into points and graph them, we find at -3, we're up here at 3. At -2, we're at 2. -1, we're at 1, 0, 1, 1, 2, and 3. So we find that when we manipulate the x value with an absolute value sign to get our output, we end up with a V shape in the graph. Anytime you see an absolute value and you're graphing it, you should end up with a V shape. We call these functions that we're graphing on this page parent functions because parent functions have no numbers inputted to change, just the raw manipulation of x. So we're seeing the most simplified excuse me. We're seeing the most simplified manipulation of absolute value x. the way I describe that graph is a V shape. Again, we'll come back to domain and range in a minute. Now we are to the quadratic transformation. Let me scoot it over just a bit so that you can see. With the quadratic, we end up taking the x and we square it in order to get the y. So we input the x, then we square that value, and we get the y. So we input -3. -3 times -3 is positive 9. -2 times -2 is positive 4. -1 times -1 is 1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. So when we come over and plot these as points, we go -3 up to 9. Now I find on this one it's a lot easier just to plot the symmetrical point at the same time. Since we know -3 is 9, we already know from our table +3 is 9, I just put them right across from each other. -2 is 4, and right across from it is +2. -1 is 1, across from it, +1, and then 0. And what we notice here, we don't get a V, but we get a U shape. And that's what we explain in the shape. Next page, this is page 2 really, but it's marked as page 1. It's page 1 of the actual note taking. You have a cover page. Okay, next page, page number 2. On page 2, we're asked to do one more graph. This is the cubic transformation. And what we're doing is we're taking x and now we're going to cube it to get y. So we plug in our x value. -3 times -3 is +9 times -3 is -27. -2 times -2 is +4 times -2 is -8. -1 times -1 is +1 times -1 is -1. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 is 9 times 3 is 27. So when we go to plot this one, what we notice is in the positives we have 0, 0. We have 1, 1, 1. We go up to 2, 8, and then 3 is obviously off the graph up there at 27. So we end up seeing it's almost like that U shape of the parabola, a little bit steeper there. But the interesting effect, instead of this coming up on this side with the U, because it's cubic, it allows for us to see a negative output. And so that side that would come up like that instead flips down, and it's like that quadratic has a twist right there at the vertex. Vertex is a turning point of a graph. Okay, so I refer to this when we're talking in class, I refer to this as the S shape. Okay, so now let's take a look at domain and range. You notice that we left all those blank. Let's just simplify this domain and range just a little bit. Let me come out. Whoa, you guys are so good at these cameras and they challenge me. Domain is your x. We talked about that when we were talking about points and functions. Domain or domain in the front of the pair, domain, and then the range. Okay, on a graph, so the domain goes with the x-axis, it goes side to side. So if we're looking at your linear function, the parent function that we just looked at, we've got a function that's going forever and ever out that arrow, forever and ever out that arrow that way. Domain means that we want to know where are the limits to this graph. So we bring it in side to side because that's the direction of the domain is side to side with the x-axis. Now we ask ourselves, is there anywhere at which this graph stops or goes no further. Well, that arrow is saying, no, I'm going to keep going. We have to let that one down. And this arrow going this way, there he is, he's pushing us out. We have no limitations. So when we get to the linear function for domain, coming back to page 1, the domain, and I just mark it with a D, is all real numbers because it goes forever and ever, left to right. Okay, now let's look at the range. Well, the range is our y values, is the dependent variable. And when we bring in our restrictors, and we say, okay, can we restrict this graph at all? When we let up on this side, we see the arrows pushing it out. There's no restriction there. When we let up on this side to see the restriction, oh, that arrow's pushing that one out as well. So for linear, your domain and your range is all real numbers. Let's take a peek at absolute value now. For the absolute value, we would end up, and you don't have these sheets, you can make a note in scratch paper if you want. In absolute value, we have that V shape. Now, going side to side for the domain, we're going to stop these walls or these edges if the arrow doesn't push it out. So we get out here to the side, that arrow's pushing it out. So there is no limitation on that side. Now this one, as we come out, is the arrow going to push it? Yes, the arrow pushes it out. So for the domain, for absolute value, back to page number 1, the domain for absolute value is all real numbers. Always in math, look for the patterns. We've got absolute value of all real numbers on both of those. Now let's look at the range. Range, again, is with the y-axis. It's up and down. So we fold them in. Fold them in. And now let's start with the top one. As we come out here, can we keep this restriction on the graph? The arrows say no, they're going to push it off the top. So there is no restriction on the top. However, when we come down on the bottom, do you notice where the arrows don't push that out? We can keep it restricted. That restriction can lay right there at 0, 0. That's where the graph touches. Because the graph touches 0, 0, we do indicate that it can be equal to 0 on the range. Y can be equal to 0, and I'd put double if I wasn't going to put an inequality here, but we also need to say that y has no limit on the top. So y can go on and on forever. So y is equal to or greater than 0. Now, I want you to get used to interval notation for your next class. So I will also write here another way that we can note this. Interval notation just uses symbols. It shows your lower number if there's a limitation, so it was 0. And then your upper number, well, there's no number because it goes on forever, so that's infinity. Okay, now we can never reach infinity because it's not a number, and if it's an open circle or unattainable on the graph, it would be a parenthesis. With 0, we can attain it. We can be equal to 0, so we put a bracket around that one showing it can be equal. That's interval notation. I just want to introduce you to that. Okay, so now our next one is to discover the domain and the range for quadratic. If you remember right, the quadratic is that U shape. And on the domain, we bring in our walls that we would like to keep side to side. And we see, oh, that arrow is going to be pushing it out as it goes up. It pushes out. And this arrow, as it goes up, it's also pushing out, getting bigger and bigger. So there is no restriction on the domain. It'll be all real numbers. On the range, you're probably already going ahead of me. As I fold this one up, the arrows push it off the top. But just like with the absolute value, you notice that you can bring this border in and it can set right at 0, 0. So for our quadratic, we know that the domain was all real numbers. There's no limitations. For our range, we could see, yes, we can bring in that border clear up to 0. It can set right there where the graph touches 0. And we can say it's equal to 0. The upper limit goes forever to infinity. Okay? Our last graph to look at domain and range, and then we're done. You guys have been fantastic today. Thank you for listening to the video. Thank you for taking notes. Make sure you always keep the sound on to listen to the instruction, otherwise you're receiving none. Because in the room, I'm coaching you. So, the last one is cubic, and it looks something like this. Now, when we bring our domain restrictors in, side to side, we see that that arrow is going out as it goes up, so it's going to push that one out. Going out as it goes down, it's going to push that one out. So our domain is all real numbers. In our range, we come from the Y restrictors, the up-down restrictors, and we see that as we fold this in and try to expand it out and keep the graph limited, the upper one pushes it out, that arrow's going on forever and ever, and the lower one pushes that out. So our range is also all real numbers. So, domain, this is for your cubic. Domain is all real numbers. Range is all real numbers. And to show you just the interval notation, you'd have negative infinity, positive infinity. Okay? So, take a look back over those. Which ones are similar? The domain, the range, which have the same domain and range and why, and which ones don't. When you come to class, I would like you to do the domain and range activity, and I'd like to have you graph just a few shapes for me when I give those to you. So we'll see you in the next video. That was video number 1.